Alrighty, guys, can you hear me? Great. How are we doing? Are there any questions before we get started? Yeah, are we good? No questions? Otherwise, let's continue. So what we've been doing, is talk about omega FP. So we have this is our set, this is our probability space. Right, so this is a set of points. Then we have F. This is our sigma algebra. And we have our P. This is our probability measure. So these are the ingredients. This is called a probability space with its sigma algebra, and P is this probability measure. And so a sigma algebra, remember, it has properties like omega is in there, so that the space itself is an element in F. We have that if we take a set in there, we're also going to get its complement to be in there. If I take a sequence of disjoint sets, disjoint measurable, well, then we're going to get that the union is in there. So we have a space, we have a system of subsets of that space, and then we have a probability measure. The probability measure, well, this is has domain f, so p is a function from f to 0, 1. It has the property that p of omega is 1, and it should not be disjoint here. If n's are measurable, sorry, if n's are measurable, take the union, I get something in there, and here is where it needed to be disjoint. If n disjoint, if n disjoint, if n measurable, then the probability of the union is the sum of the individuals. So up here, we don't have to have this disjoint. This was a mistake. Arbitrary countable collection of sets in F has the property that that union of them is going to be there. And then this, when you want to check whether or not a function with domain F is a probability measure, you need to check these two. So you have to have that omega has probability 1, and you have to have the disjoint sets. When you add up the probabilities of these disjoint sets, you get the same thing as the probability of the union. But just as for similar to the sigma algebra having properties like if I took instead of doing unions, you can also do intersections. So even though the sigma algebra is not defined using the intersection property, we talked about that it actually also has this intersection property. So whenever I take sets in F and I do the intersection, I actually get that that intersection is also in there. Probability measures have more properties. So let me look at one that we're going to be using. So for example, we call this a little lemma. If I take fn, so you need to be measurable. Okay, so we got that. And then we take an increasing sequence. So I take fn is inside fn plus 1. Is inside fn plus 2, and so on. I take an increasing sequence of sets. Well, then, if I am to compute the limit as n goes to infinity of p of fn, so these sets they get bigger and bigger and bigger, and I'm interested in computing the probability, the limit of the probabilities of these individual sets. What could it be? Any guesses? Someone a picture. Switch the probability and the limit. Yeah, so this is, so the problem is we do not have, there is no f infinity. Okay, so there's no, if we have fn in f, this here is for n in the natural numbers. Right, so there's no f infinity because infinity is not an element in natural numbers, so we cannot do that. but the idea is right. What is it we're going to get in the limit? We somehow want to pull this limit inside P, but we don't have an F infinity. But what could we write instead? It's going to be P of something. What could it be P of? Right, so the idea is right. So we have our space. This is our space omega. And then what we're looking at, this is our Fn, and then we're going to do a bigger one. This is our Fn plus 1, and so on. What is it we're going to get in the limit? Not necessarily. So we're going to get, there's no guarantee that we're going to get omega, because they could stop here, right? They could grow up to this one, smaller and smaller and smaller. We don't know that the Fn's are going to fill up the entire space. The thing we're going to get here is the union. The thing is, we're going to, yeah, so exactly, the union of the F's. Very good. Very good. So how would one go about proving something like that? What would be a proof of such a lemma, saying that I have an increasing sequence of sets. I am, when I compute the limit of this probability, then I'm going to get this probability of that union. And the only thing we have to go by is these two properties here. So we need to do something about disjoint sets. Okay, so the way that we're going to start is by redefining these sets. So we're going to define, let me put tildes on top of them. So f tilde 1 is going to be f1. And then I go all the way down to f tilde n is going to be fn minus what came before, fn minus 1. Right, so if this here is my first one, this is going to be my first set. And then the difference, this part here, this is between fn and fn plus 1. That donut, this is going to be my fn tilde, fn plus 1 tilde. These ones here are disjoint. These are disjoint, and the disjoint sets, and if I'm looking at the union, if I'm looking at the union of the tilde ones, if I'm looking at the union of the tilde ones, I'm just going to get fn. So this is if I take a finite union, I'm just going to get, every time I get a bigger and bigger donut, and when I union them all up, I'm just going to get the original set fn. And similarly, if I take a countable union, I'm going to get exactly the same as the union of my original ones. And the benefit of working with these tilde ones is that they're disjoint, whereas the f's themselves, the ones without the tilde, and they are increasing. And so now I can use, now I'm allowed to use this property here for the f tilde sets because they're disjoint. So I'll do that. So because if tilde n disjoint sets, we can use the property. So I'll start by computing the probability of Fn. This is going to be the probability of the union. Okay, so that was that equality sign. Now these guys are disjoint, so I can call the sum up sign. So this is because they're disjoint. Then I can take a limit. I have a bunch of positive numbers here. I compute the limit. And these are as a function of n. Because all these numbers here are positive, as a function of n, this is monotone. And so there is a limit. So I can take the limit. This is going to be the sum from 1 to infinity of p of fk tilde. And then I use a property over here. This is exactly the same. This is exactly the same as what? So I need to move the sum inside. I can do that because the tilde is the disjoint. So I get the union from 1 to infinity f tilde k, and then I use the property that this is the same as p of fk. Right. So even though this property here that we had in the lemma, even though this property here is not listed as one of the defining properties of what it means to be a probability space, this property here with having the probability of a disjoint union of sets, having a union of disjoint sets being just the probability as the probability is summed up, that property will allow you to say that, well, I have this monotonicity property that if I have increasing sets, then the limiting probability is just going to be the probability of the union. And likewise, we can do similar if what do instead, we would say instead of fn being increasing, we would say that fn being decreasing. So if we have that, and we're interested in the probability of fn, and then taking the limit, any guesses on what this limit is going to be now? Flip it around, so I have a decreasing sequence of sets. So as n gets bigger and bigger and bigger, these sets they get smaller and smaller and smaller. What do we get here? Any guesses? We're going to get the intersection of f's. Yes. So when it comes up in the chat, it is not always showing up on my. It's not always showing up on my screen. So if you're writing stuff in the chat and I don't react to it, just unmute yourself and then you're welcome to unmute yourself and speak out too. Sometimes it doesn't show up in the chat. So it says the intersection of the f's, and that's absolutely spot on. We're going to get that this here is the limit. The limit of these probabilities is going to be the probability of that intersection. Does disjoint mean mutually exclusive? So a sequence of sets Fn is disjoint if Fn intersection with Fm is empty, as soon as you take two indices that are not the same. All right, so this was a little bit, so we talked a little bit about, probability measures, but maybe we could be interested in like, so what is a good example of a probability measure? We talked about some last time, so we talked about, last time we discussed the back measure on these Borel sets, 0, 1. Let's try another one. This is something that comes up mainly, already come up in your homework. So here's another example. Distributions. So a distribution, right? You take a random variable. So this is my x. We'll talk a lot more about random variables in just a little bit, but let's just for now, x goes from omega and say into r. Distribution. So you take a function, domain is omega, take values into r, and then you define the distribution function. Maybe I should call it something else than f, because those were the sets we were just playing with. What should we call it here? What do we call distribution functions in the homework? What did we call them in the homework? We had something in homework too. Did we not call distribution something? We called it density for little f. What did we call the distribution? We didn't call it anything. Huh? Okay, so I needed a letter for the integral little f. L, that was the Laplacian. We don't want to use L. So I don't know. Let me call it mu. So mu of x. Mu of x. This was our distribution. This was the probability that x was less than x. We could do this more generally, or more generally. We could say mu of b. This could be the probability that x belongs to b for a Borel set. Right, and then you get the first one. You get the first one by, so these are consistent. So by using b to be, we want x to be, so we want to look at minus infinity to x. By using this for x in R, we'll see that the mu of that interval this is the probability that x belongs to that interval. And this is the same thing as the probability that x is less than x. Right, so this is really more general. I can get the first one simply by considering b of that particular form. So the cool thing is that, so you give me a random variable and I look at this distribution here. This is a probability measure. So this is a little lemma. And mu is another probability measure. On these Borel sets. And it's not so hard to see because we need to prove two things. We need to prove that if I put in omega, that's the whole space, I get 1. And I need to take disjoint sets. Well, then the probability of the disjoint union is going to be the sum of the individual probabilities. So I need to check these two properties. Okay, so first, what is my omega here? If I want to have 0 and 1 here, I should probably put 0 and 1 here. Otherwise, you'll have to put r here, and you'll have to put r here. Okay, so in this case, my omega is 0 to 1, so I need the probability. I need mu of that interval 0 to 1. I need to check that this is equal to 1. But I just used the definition. This is the probability that the random variable is less than 1, and that was given, right? Because x has domain omega, it takes values between 0 and 1, so this here is 1. If I take disjoint sets, with disjoint sets in this interval, then what I want to do is I want to take mu of that union. I want to take mu of that union, and well, I use the definition. This is the probability that x belongs to this union. And now I use the fact that the probability that x is in this disjoint union, this is going to be the same thing as unionize and then asking for x being in B. And then I use that. I'll use that these are disjoint sets because the BNs are disjoint sets. I'll pull it out. I'll get the property that I want. So this mu here, this is really a probability measure on 0 to 1. So you can also, this can be extended. That was the one I had written first. So if I look at x going from omega to r, well then the distribution mu b being defined as the probability that x is in B, but now for Borel sets on the real line is a probability measure. So we've seen a couple of examples now of probability. So this measure here, this will satisfy the property that, for example, this measure here would satisfy the properties that we just had, where, for example, if I have a decreasing sequence, the probabilities converges to this intersection. The one before was that if I had an increasing sequence of sets, then those probabilities here will converge to the probability of the union. And this will be true for all probability measures. In particular, it will be true for probabilities that I can construct using random variables like x here. Yeah, are there any questions so far? Well, guys, the next goal is to talk about. So now we talked about the measure space, this probability space, and the next goal is going to be to talk about integration. And the next steps. The next, so our goal today is to define quantities like E of x and a quantity like E of x given G for G being a smaller sigma algebra than F. So F here is always going to be that F we start out with. And so G is going to be something here that is a smaller sigma algebra than F. So we want to define these two quantities, like this is an expectation, and this one here is a conditional expectation. So this is called the conditional expectation of x given G. Right, and we have a random variable here. Is this to define for a random variable x going from omega to r. So I have a random variable. I want to talk about its expectation. This is the expectation. This is the conditional expectation given a sigma algebra. So you probably have seen. Do you have probably? You've probably seen that if I am to compute an expectation of this form up here, I would write this as an integral over the codomain of x, and then maybe you put in a density m of x dx for a density you've also probably seen so you've probably seen this. You've also probably seen you've probably also seen that the if you are to compute an expectation of x, say, and then given y being some a conditional expectation of x given y is equal to y, there's a formula here when x and y, thank you, have a joint density. So what we're going to be doing here is not going to be relying upon having these density functions. we're going to have like the general form expectation, we're going to have a general form of the conditional expectation, and the most general one we can come up with is this E of x given g. We don't have densities when we're talking about these binomial models, right? Because we have a random variable that takes only two values. So we have a random variable that takes on only two values, it's not going to have a density. So we don't have these joint densities. We don't have a density in general. So this is a little bit involved getting this stuff written out, and yeah. So this is what we're going to be spending today doing. So the first thing we need to do is to put more structure on these functions here. So the first notion that we're going to need is measurability. So we write what that is. So we say that x, so again, it's a function. We say that this is measurable. This is also called a random variable. We say that this function, x, domain omega, codomain r, this is measurable if I look at the set x less than x, if this belongs to f for any x in the codomain, which is r. And you can see this is really needed because we already worked with it on one of the previous ones. Like here, I'm writing the distribution function. The distribution function is x less than a constant. So for this to make sense, I need this set here to be in P's domain. And P's domain is f. So for this to make sense, I do need to have this product. And so that's what it means to be measurable. On the other hand, sigma of x, so that's again this sigma notation. This denotes the smallest sigma algebra, such that these sets here, they are in there. One can generalize this. So more generally, if x1, x2, and so on is a sequence, well then if I look at the sigma algebra generated by, say, the first n, this one here, this denotes the smallest sigma algebra, such that these sets xk less than x belongs to x1, x2, up to xn for any k and for any epsilon. So this looks pretty abstract. It can be a bit much to take in. But you see, this here is really what we need in this class. So we think about, for example, these x's here as being the outcome of coin flips. And so when you have a multi-period binomial model, then we'll see over time the outcome of these coin flips. So this n here, we're thinking about that as time. So this x1 will be the outcome of the first coin flip, x2 will be of the second, the third, and the fourth, and so on. And so over time, we'll see more and more coin flips. And so we need a way to store that information. And the way that we're going to store this information, keep track of it, is by using sigma algebras. And so here we have a sigma algebra that is indexed by n. And such sigma algebras here are called such collection of sigma algebras that are indexed by n, and n being how much information you've seen, and that's called the filtration. So we note here that this sigma algebra of x1 generated by x1 up to xn, this is inside the one that goes up to xn plus 1. Like there's more information over here than there is over here. And this aims to model that we have seen one more outcome than we have over here. So let me try to illustrate this in a specific example, so we can see what's actually going on in a specific simple setting, which is relevant to our binomial model, right? So we're looking at a very simple one. Let's just do a 2-period model. We had looked at some point, we had looked at a model where this stock price would go from, say, 4, it would go up to 8, we go down to 2. We had seen that one. So let me make it, instead of just having a 1-period, let me make it a 2-period model. So over here, we will allow it to go up to 16, allow it to go back down to 4, allow it to go back up to 4, and allow it to go back down to 1. So we do a 2-period model. So here our omega is going to be the 4 paths. So it'll be heads, heads, it'll be heads, tails, it'll be tails, and then heads, and tails, tails. Right, that's my omega. And my probability measure P is not even needed here, right? There's no mentioning of a P anywhere in this discussion of measurability, so we don't have to specify that. We have to specify what F is. Okay, so let me do F. This is just going to be 2 to the omega. This is going to be all omegas subsets. Okay, so that's a big collection. So you form all kinds of possible combinations of these ones. And so now we want to look at, and this is my stock, right? So this is S0, this here is S1, this one here is S2. So the stock price starts at 4, then it goes to either 8 or 2, depending on the first coin flip, and then it goes further depending on the second coin flip. And now we want to know, if I'm looking at the smallest sigma algebra that makes, say, S1 measurable, what is it? And what's the smallest sigma algebra that makes S1 and S2 measurable? So this is our model. We have this is our 2-period binomial. This is a 2-period binomial model for the stock. It starts at 4. It can either go up or down, and the same thing is going to happen in the next period. It can either go up or down. And I'm interested in what is the smallest sigma algebra that makes S1 measurable? What is the smallest sigma algebra that makes both S1 and S2 measurable. Right? Keep in mind, the sigma algebra is a collection of subsets of the sample space. Sample space here means omega. Right? So we need to form subsets of this these four elements over here. There's going to be some description. We need to figure out what it is. So the way to do it is you go back and you look at the definition. What does it mean to be measurable? Well, it means that these sets here, x less than some the random variable that you're interested in being measurable, you put it to be less than something in its codomain. And okay, so if I'm looking at S1, there are values 8 and 2. So if I'm looking at the set, when S1 is less than, say, 10, what do I get? What omega is up in my sample space is going to make it such that S1 is less than 10. Start out with, try one of them. If I take S1 at HH, if I do S1 of HH, I get the value 8. So 8 is less than 10. That means that HH is in here. What happens if I do HT? If I take HT, plug it into S1, what is S1 of HT? It's going to be heads and then tails, but I'm only interested in the value it has here, so that's 8 again. 8 is less than 10, so I'm going to get HT is in here. What happens if I do tail heads? What is S1 at TH? Well, this one I only care about the first coordinate. The first coordinate is 2. 2 is less than 10. Okay, so that's in there. And TT is going to be the same. TT, go tail, tail. I'm only interested in the first one. 2 is less than 10, so that's going to be in here. All right, so that's my omega. No matter what element in my sample space I'm looking at, S1 is less than 10. Okay, so that has to be inside that set. What else could I look at? Try to get something to maybe have a more complicated structure, right? The value is 8 and 2. So if I go down and look at S1 less than, say, 5, what would we get now? What would we get now? Yeah, TH, TT, very good. We're gonna get the last two over here. Very nice. Ah. And then we should also just for good measure, let's put in a value. Let's put in a value that is down here. So let's do like S1 less than, I don't know, minus 10. What do we get here? Yeah, so the null set, nothing. Null S. That's very good. So what I don't like about this null set, and I will have a discussion about this in a little bit, there is a difference between null sets and this what Sharan Wang is saying, nothing. I like the word nothing a lot more than the word null. I call it the empty set. And this is, so null sets are not always empty. So null sets, they have to do, null sets, they involve the measure. And null sets have to do with whether or not the probability, if it's a measurable null set, it has to do with whether or not the probability of that set is 0. Whereas the empty set always has probability 0. And here we haven't specified what P is, so I don't like to talk about null sets here. We get nothing. We get the empty set. And then I'll define. We will define this. We'll define null sets later today. I don't want to introduce a measure here because it's not needed. So very good. So what does that mean? So there's all these things here. That guy, and that guy. They all have to be in here. So sigma of S1. I'm trying to write out what it is. So it's going to be omega. It's going to be the empty set. It's going to be this one. What else? Is that good, or do we need more? Should we put a bracket here, or do we need more stuff in the sigma algebra? Well, keep in mind the sigma algebra has these properties. Like it's the smallest sigma algebra such that something holds, right? So now we have all the sets in there. That's good, but is it a sigma algebra? We need to put. We need to make sure that. The properties of being a sigma algebra are satisfied, right? So we need to have omega in there. That's good. We have omega in there, so we save there. We need to have the complement property in there. Okay, and the complement property we don't have, because if I look at the complement of this one, the complement of this one is not in there. So I also need to have a complement to make it a sigma algebra, and the complement of the set here is the thing that starts with H. This is H, 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 T. And now I think I'm good because I'm stable on the complements, and I can also take arbitrary unions. I always stay in here. So this here is my sigma of S1. And then we should try to figure out what is sigma of S2. So what about sigma of S2? S1, sorry, sigma of S1 and S2. Well, one thing we do know is that it has to contain all this stuff because it has to make both S1 and S2 measurable. Okay, so at least I need to put all that, whatever I have here has to go in there. So this will be omega, empty set, TH, TT, H, H, HT. And then it has to have the property, but there's probably going to be more. There's probably going to be more stuff in here, and I need to figure out what more stuff it is I have to put in there. So the defining property again is what? I need to have the property that if I'm looking at a collection, I need to be able to take each individual random variable in that collection and look at those sets, and they have to be in there. Right, so now I checked it out with x1, I need to move on to it, but not x1, s1. I did it for s1, I need to move on and also do it for s2. So let's try to put some of those over here. So let's look at a similar calculation, but instead of s1, I'll look at it for s2. So s2. Maybe we can use the same numbers. If s2 is less than, I don't know, what could we pick? S2 can have values 16, 4, 4, and 1. So if you start out with 20, if I start out with 20, what do I probably get? I look at what are my elements here, these 4 guys. When I plug them into S2, I'm going to get something that is either 16, 4, 4, or 1. Everything there is less than my 20. So I'm going to get omega here. Excuse me. Okay, so let's see if we can get something that has a little bit more action. Pick something in between 16 and 4. So maybe if you pick I don't know, S2 less than, I don't know, 11, what would we get here? So I'm interested in what omegas, what elements in my set omega will produce S2 to be less than 11. Well, now the first one is ruled out. The first one here is ruled out because that will give me 16. And so the remaining 3 will be HT, TH, and TT. It'll be these 3. And when will I get something next time? Probably put a value in here somewhere, like a 2. If I put a value of 2, I'll get something else. So I'll put in a value of 2. What will that give me? So if I look at 2, 2 is here. So I want S2 to be less than or equal to 2. That's going to leave me with just TT. So all these things have to go up here as well. Okay, so let me write that in. So we already have omega. And then we're going to get HT, TH, TT. And then we're going to get TT. So they all have to be there, otherwise it will not work. But the question is that a sigma algebra? It has the property that all these sets are in there, but does it also form a sigma algebra? Well, what we talked about last time is that a sigma algebra has to be stable under all kind of countable operations. So you have to be able to take unions, intersections, and differences. So for example, if I would look at these two sets, I have to be able to take a difference. And they're complements, exactly. So complements, intersections, unions, focus just on differences here, right? I take this set, subtract this set, I'm left here with, what will be, TH. And if I look at, what else could I look at? What could I look at? I look at this set over here. This set I have TT and TH. TT and TH. If I subtract them away, I'm going to get HT. That has to be in there. Okay, but then I can subtract HT away from this one, and I'm going to get HH. Then I also need arbitrary unions. So then I would need to be able to do arbitrary unions of these. So I keep going, and in the end, I'm going to get 2 to the omega. Like, I have a finite probability space, and I have every single element in my sample space is there. Well, then I have to be able to form arbitrary countable unions, and so that's going to get me all right. So this was one example of how these sigma algebras could look like. So what's important is that they grow in size, and this is often denoted by Fn. And as I said, this is this one here. This is so I have this is my Fn, and this one here. This is my Fn plus 1. And this is a filtration. And this will be the way that we model the flow of information. So when you move from, where was it? Here. When you move from having observed one coin flip, this here is this is going to be modeling your knowledge as an investor, this sigma algebra. And then when you see the second coin flip, you're going to get something that is bigger. And in this particular example, it's going to be much bigger. And then you're going to learn a lot more. You're going to learn everything that is inside that. So this is going to be our way of modeling the flow of information. So we model the flow of information by filtrations. Where S is the stock price. Okay, are there any questions here? Any questions or comments about what we just talked about?
I want to ask the question about the 2 omega. Why is 2 omega?
This one? This is just
Yes.
this is just notation. So 2 to the omega denotes the set of all omegas subsets. Some people write it as P of omega, the power set.
Which means that it is just a signal.
Can you say that again?
It means that the 2 to omega is just a signal.
A signal? No, yeah, it's just, this is just notation. This is just,
Okay.
this is just notation.
Okay. Thank
It doesn't, however you write, a set of all subsets, you can write it as P or as 2 to the omega. This 2 to the omega, this has, the reason that it's written 2 to the omega, the intuition behind this is that if I have a sample space with 4 elements, and I want to know how many elements there are in a set of all possible subsets, you're going to get something like 2 to the 4. Like, for
Oh,
example,
so I mean,
Yep.
so 2 to the omega is the total number of the subsets of a set which contains the sigma number of the elements.
it's not the number. So 2 to the omega denotes the set of all subsets.
It's a set.
It's a set, yeah. It's a sigma algebra. It's the biggest sigma algebra that there is. Right? So it's just that the symbol 2 to the omega, the reason that it's written this way is it's just to remind you that, well, if I were to count how many sets there would be in this collection of subsets, you would get exactly
2 to the omega.
when omega is finite. Right?
Okay.
When omega is infinite, then that's a different story. But you can also, if you find this confusing, you can write it as this one here. Or you can also just not write it and just say the power set. Omega. More questions or comments? Then we'll move on. So again, keep in mind what the goal is. Should always keep in mind what the goal is. The goal is, so now we know what a random variable is, and it's a measurable function. And so now we're going to be interested in taking the expectation of a measurable function. So we'll always have, going forward, need more paper. Going forward, when you see this symbol, when you see this will be a measurable function. Like this symbol here, this just means, strictly speaking, a function. This here means a function. But we're going to have this additional property that it's going to be measurable. So, and we'll talk about, and we always mean a measurable function when we say a random variable. Which this is just a disclaimer. Like, so when we talk about a random variable, so that's going to be a function which is measurable. Okay, so now what we want to do is we want to define, we try to give meaning to the Lebesgue integral, the the Lebesgue integral, this is this expectation. What is this equal to? Well, there are many ways to write it. So the Lebesgue integral can be written many ways. So probabilists divide this expectation. In the old days, there was a debate about whether this should be called E for expectation or it should be called M. So if you find a really old textbook, in particular from the Russian school in probability, you will see that this E here is actually M. But anyway, I'm just going to write it here in a bunch of different ways that you sometimes are going to see. They all mean the same. So you'll also see this here written as an integral of x, then this dp. You'll see it written as an integral of x of omega, and then sometimes you put omega down there. And then you would write it as dp of omega. And some people like to swap these two, and you write it as an integral of omega of x, and then it'll be p of d omega. So you'll see this probabilist, and that's going to also be what we mainly do in this class. We will write this here as an expectation. We won't write that out like that. They all mean the same. There's nothing, these symbols, they all mean the same. And it's that symbol we're going to try to define precisely what it is. Right, so this is not the Riemann. This is not the Riemann integral. But because we have this abstract omega, this is not the Riemann integral where you have f going from, say, I don't know, 0, 1 into r. And so you have an integral from 0 to 1 of f of x dx. And these two objects are not the same. They're not the same. And it's also a bit unfortunate that when you write in calculus, you typically see the functions are denoted by f, and the dummy variable is denoted by little x. Whereas in our class, the functions are denoted by capital X, and the input parameter, the dummy, is denoted by little omega. So that's unfortunately how it is. It's rare that you see in calculus that the integration variable, the dummy here, is going to be an omega. You will not see f of omega d omega. This is typically not something you see in calculus. But these integrals are not the same because the domain, this here is this is what you need for the Riemann integral, and what we're going to be having is this abstract omega, which is not specified. This abstract omega, it could be this thing here, and it could be something much more general. So we are interested in figuring out, we're interested in defining this expectation here and then looking at some of its properties. So how to get started? Well, one thing we could do is you start out. So let's start with what's called simple or elementary random variables. These guys are like x. So this is my random variable. X of omega is defined to be, say, 1 if omega belongs to some set A, and 0 if omega is not there. This is for a set A inside omega, and A belongs to F. Start out with these, and this here is also denoted. This is very often denoted by the indicator. So this is a 1 of A of omega. This here is the indicator. This is the indicator function for A. So what happens is my sample space is illustrated with this set here. There's a set A. A could be, I don't know, something like that. On these two, this is my set A. It's these two pieces. On these two pieces, my random variable is equal to 1, and outside these two pieces is equal to 0. And that's my indicator function. So the first thing I need to do, this is the way that one creates the Lebesgue integral, this expectation. The first thing I do is I give meaning to what the expectation is of such a thing. So what is the expectation of an indicator? What is that? So this here is a definition. The expectation of an indicator, well, on the set, the random variable has the value 1. So you're going to take 1 times, and then how big is the set over which it's 1? Well, how big the set is, that depends on how we measure the set. So this is going to be times P of A. So this is P of A. So we define the expectation of an indicator simply just to be the probability of the set. That was step 1. So now step 2. Step 2 is what happens if, so more generally, what would happen if my x of omega, would be, say I sum up from 1 to some constant m of yi times indicator of ai of omega, where I'm keeping the yi's positive just for now. So the yi's here between 0 and infinity, the constants, and the positive. And the AIs, they're going to be just like we had up before. They're going to be measurable subsets of omega, and they're going to be disjoint. AI intersection with AJ is going to be empty for any I that is not J, right? So here the situation is, this is my omega. I'll have a corner here. This would be my A1, and this would be my A2, and here I could have A3. And then I'll have a bunch of constants. And so on these cells, on these disjoint sets, on these blocks, whatever you want to call them, on these partitions, partitions probably, that's not a good word, because partitions would somehow indicate that when I take the union of all of them, I'll get omega. This is not what I'm saying here. I'm saying I take these cells, and on these cells of omega, the random variable that I call x, it's constant. So how would I do the expectation now? So the expectation of this random variable is going to be the expectation of x of omega. How will we do that? Well, this is going to be the yi's are constants. We want the expectation to be linear, so I'll pull out the finite sum, and I'll pull out the constants. And then I'll use that the expectation of an indicator. This is exactly the probability of the set. So this is going to give me a number between 0 and infinity, because the yi's are all positive. I'm going to get a number here. I'm going to get the sum of these yi's, and then they're going to get weighed with the size of these sets ai that I have. Okay, so that's how we do. That's the starting point of describing the expectation of a measurable function, a random variable. We start out by assuming that it has a much simpler structure, namely just an indicator, or more generally, having it to be a sum of indicators for discharge sets. And now the question is, how do we extend this to the general case? So I think it's a good time to take a little break. So after the break, so next we're going to extend to the general case. Okay. Are there any questions before we take a little break here, and then we'll get started back up around 10 o'clock? Are there any questions before we do that? Yeah. Are there any questions before we do that, or should we take a little short break and then get back together? Remember, we have to switch over to a different Zoom link. Okay, if there are no questions, then I'm going to end the video here, and then we'll get back together in like 10 minutes or so on a different Zoom link. Okay, I'll see you guys shortly.